design constraints, but some people tend to call it standard design constraints, primarily the non-Synopsys EDA vendors, because it's not really a standard, as in, it's not an IEEE standard. We'll talk about that the next couple of slides. So the SDC standards library on the RTL design, these are the three inputs. Your HDL synthesis tool. It could be, of course, the design compiler, Genus from Cadence, or Vivado, or Fortness, or it could be an open source tool such as Yosis. Right? So what comes out of the synthesis tool is your netlist. Again, most likely it's going to be a very long or system Verilog netlist, but here there are also VSTL netlist writers. Right? If you stick to a VSTL flow, you feed in a VSTL or TL and spit out a VSTL netlist. That's still possible. Right? And it also writes out the post-synthesis SDC, though our focus is going to be at the pre-synthesis side. But a lot of techniques that we talk about in this whole training is equally applicable to a post-synthesis SDC as well. Because the design signal names could have been changed, some signals may be gone, there's a mapping and all that stuff. So there's a post-synthesis SDC is as good as pre-synthesis SDC for us from pure verification perspective. Right? In fact, post-synthesis netlist goes along with the post-synthesis SDC. And of course, you also get a PPA report. PPA stands for power, performance, and area. And you want to know whether you met all your constraints. That's the typical HDL synthesis flow. So what's the role of SDC in chip design? The functional part of your design is captured using Verilog, System Verilog, or VSTL. Of course, as I mentioned, in case of an IP that is written using VSTL, it can be integrated to a SOC, which majority of the blocks perhaps are Verilog and some are System Verilog, some are VSTL. Mix and matches the reality of today. But what about timing part? The timing specification is important because it's not enough for a design to work correctly. It must also meet the timing requirements. There are also delay paths. At RTL level, we really don't accept a lot of delay calculations because we tend to say register to register, and hence it's called RTL. But then there are critical paths that must be analyzed to ensure delays are within acceptable limits. Again, we are not going to do the traditional gate level with STF in this particular context. We're going to talk about an abstraction level timing, wherein, for example, the set input delay, set output delay, set max delay, certain things that if you want to verify, how do you verify? But more importantly, from a SDC perspective, what are the false paths? What are the multi-cycle paths? What are the timing exceptions that you want to verify? Because these are abstraction level, and you could actually verify a lot of that at RTL level. The key objectives of SDC is to ensure the design is functionally accurate. Also, to ensure all operations meet the required timing performance. Otherwise, your chip, which is intended to be run at, let's say, 200 megahertz, may not actually work, and you will have to reduce your speed to, let's say, 150 megahertz, which is quite less compared to what your customers expect. So, if you want an analogy, RTL captures design functionality, SDC captures your timing constraints, timing requirements. So, continuing what we are talking about, SDC's role in chip design. You use SDC to define